We're looking at moment of inertia of uniform solid cylinder. So start off with the first case. We are considering a uniform solid cylinder with mass m and the height is L and the radius is R. It's rotating about its central axis perpendicular to circular. So this is perpendicular to its circular face. So this is the circular face and perpendicular to that is your axis of rotation. So it might be rotating in this manner. Now we are making use of R square dm. So for us to integrate this, for above integration to take place, it will be convenient so how can we go about doing this? It'll be convenient to divide the cylinder. Yeah. What should we do? Into coaxial, that is same axis. So coaxial, what we have is coaxial cylindrical shell. Cylindrical then shells actually. Yeah. So basically you can imagine this and us dividing the entire thing into cylinders in this manner. Hollow cylinders basically of varying radius. The height will not change, the radius will change. Okay, so you can imagine that. Things like this. So they are hollow. So basically we are considering the thinnest one. The length will not change. I'm just drawing small and a bit larger, a bit larger. Radius will not change actually. So a bit larger and so on and so forth. And so on and so forth. Okay. So this is the case. Now we'll consider one of it. So consider one such shell of radius r and width dx. And then what we have is here r will be r for me. The distance is fixed, that's r, while my dm, which is given by, in this case, it is volume or density into volume. That's equal to mass. Okay, so we are making use of this actually. That would be appropriate. So for a small density of dm, for a small mass of dm, density is m by, so cylinder area volume is pi r capital R square L, right? That's the volume times the volume of this thin shell would be pi r square square, then sorry, it won't be that, it would be 2 pi r times L times of dr. Okay, so this will give me the circle. This circle is added all along the length L and it has a width of dr. and this will give me the volume basically. So things to cancel are pi, then L, so length will not matter, and what we have is m 2m by r square, all these are constant, times of r dr. R dr is varying, it's like x dx, we have r dr. Therefore, I will be equal to integration of r square into 2m by r square times of r dr. We are integrating from 0 to end of the radius. So we have 2m r square integration from 0 to r cube dr, and we have 2m by r square times of r to the power of 4 by r, 0 to r, and this is 2, that is 1 by 2 m r square, and that would be your answer. That's it. So again, as you can see, it's the same idea. Instead of length and instead of area and all of that, we have volume over here. That's it.